Our third method, it really only works best when we have two reactants in one product. We're using conservation of mass method. So if our calculated product is greater than the sum of the reactants, that reactant is in excess. If the calculated product is less than the sum of the reactants, it's the limiting reactant. So what it does is this method lets us, instead of calculating both products from both reactants, after we calculate one, we can determine the answer right there. So if we have 200 grams of both iron and chlorine, we're producing iron 3 chloride. We have 400 grams of reactants. So if we pick iron to calculate first, we divide by molar mass, multiply it by the stoichiometric ratio, multiply it by the new molar mass, and we get 580 grams. This is greater than 400, so this is not possible. We would violate conservation mass, which means that our iron is in excess. So that would mean that our chlorine is limiting reactant. So after doing one calculation, we can see already which one's going to be limiting, which one's in excess. If we started from chlorine, we would have gotten 305 grams of iron 3 chloride, less than the 400, so that would have shown that the chlorine was limiting reactant. So one reactant is used up completely. The other reactant often will be in excess. There will be an unreacted portion of that. The unreacted portion of the reactant is called the excess reactant. So there are two ways that we can get excess reactant. The first general way that works for everything is that once we determine which reactant is the limiting reactant, we use that to calculate how much of the other reactant is consumed. And then we subtract it from the starting amount to get the excess amount. So if we're given 10 grams of both reactants here, we want to know what's in excess. First we have to determine which one's the limiting reactant. If we determine that the iron 3 oxide is the limiting reactant, now we're using this to determine how much aluminum will react with it. So we take the iron 3 oxide, 10 grams, divided by its molar mass, multiplied by the stoichiometric ratio, multiplied by the new molar mass, and we get 3.4 grams of aluminum has been consumed. So we take that, we subtract that from the initial 10 grams of aluminum, and we're left with 6.6 grams of excess aluminum. So this other method is based on conservation of mass, and it works in a limiting way in terms of it works best for when we have two reactants in one product. So after we get our theoretical yield of the product, 305 grams, we subtract that from the initial mass of all the reactants. So we had 400 grams of reactants, we subtract 305 theoretical yield off, and we get 95 grams in excess. We had to know that our chlorine is limiting. That would mean our excess is in the iron, 95 grams of excess iron. When we calculate how much product we can get from the available reactants, this is called theoretical yield. It's theoretical because in reality we often don't get that. What we get is called the actual yield. And for a variety of reasons, the actual yield is usually not as large as our theoretical yield. So we can have an incomplete reaction, not everything reacted. We can have a side reaction that produces an unexpected product that we weren't looking for. We could have just not been able to extract our product out of the reaction container, out of the solvent, or sometimes we can't purify the product properly, so it has a contaminant, it has solvent or other things in it. So a useful measure for us to determine how well the reaction is working is called the percent yield. So percent yield is going to be the actual divided by theoretical yields times 100%. We usually want or hope that this will be close to 100%, For some commercial products, we can handle a percent yield that's real small. And then if it's ever greater than 100%, it means that we have a contaminated product. So in solutions, when we dissolve compounds in solutions, ionic compounds, acids, and bases will dissociate or ionize in solution. This will create a solution called an electrolytic solution. So these will be electrolytes. Electrolytic solutions can conduct electricity. Covalent compounds, except for our acids and bases, do not dissociate in water, do not ionize in water. For our ionic compounds, what we're just going to assume, it's a generally good assumption, not perfect, is that our ionic compound will dissociate completely in water to produce cations and anions. And if we look at table salt dissolved in water, we do find essentially complete ionization of the table salt into sodium ions and chloride ions. For acids, we rate our acids or categorize our acids as strong and weak. A strong acid will dissociate completely, just like ionic compounds, but a weak acid will dissociate partially. So acetic acid here is a weak acid, and we get less than 10% ionization here, so about 90% unionized. Same for weak bases. Ammonia is a weak base that reacts with water to form the ammonium ion and hydroxide ion, and again, just a small amount of this will be ionized, and the majority will remain as the unionized ammonia. So solutions that have ions in them are called electrolytes. They conduct electricity, and those electrolytes are either ionic compounds, acids, or bases. So a strong electrolyte will have a high concentration of ions. That means a soluble compound that will ionize completely. So this would be ionic compounds with good solubility and strong acids. Weak electrolytes have poor current carrying capacity. This forms either from a poor solubility, a low solubility of an ionic compound, or a partially ionized compound, which is generally our weak acids and our weak bases. Non-electrolytes do not carry electricity, and these will be our covalent compounds that are not acids or bases. So when we look at dissolving things in a solvent, we can use the qualitative terms soluble or insoluble. And these terms do vary with our needs of what we're working with at the time. So if we have an appreciable solubility, we can call it soluble. If the solubility is minor or negligible for our needs, we can call it insoluble. But to make things more quantitative, we can give solubility a numerical value in terms of grams of solute per 100 mLs of solvent. So this will give us a better way of describing our solubility, quantitative way of describing our solubility. Solubility is also temperature dependent. Solubility of most solids and liquids increase with temperature. So as we increase temperature, the solubility increases. So that's why hot tea can dissolve more sugar than iced tea can. However, the solubility of gases is the reverse. The solubility decreases as we increase temperature. So soda water, which is carbon dioxide gas dissolved in water, will lose its fizz, go flat faster at a high temperature, and retain its fizz longer at a cold temperature. When we are dealing with ionic reactions in solution, the molecular equation is not always the best equation to tell us what's going on. The molecular equations are what we normally deal with, showing all the compounds of the reactants and products. But in solutions, what's often better for describing the actual reaction, so It gives us better clues what we can change in the reaction when we're working with it. Is the net ionic equation. Net ionic equation is showing only what's participating directly in the reaction. So to get to net ionic equation, it's a two-step process. What we're going to do is start off with the molecular equation and expand that into the complete ionic equation. So what that is all of our aqueous ionic compounds, aqueous acids, we're going to expand into cations and anions. Solids, liquids, aqueous covalent compounds will not be affected. After we expand the molecular equation into a complete ionic equation, what we're going to do then is look for the non-reacting ions. These are called spectator ions. So when we find ions that are showing up on both sides of the reaction that are not being changed by the reaction, these are our spectator ions. So in this example here, we have 2 sodium ions on both sides of the reaction. So those are spectator ions. We have 2 sulfide ions, well, a sulfide ion on both sides of the reaction. So that's also a spectator ion. When we remove the spectator ions, we're left with the net ionic equation. So the net ionic equation is showing us that calcium ion is reacting with chromate ion to form a precipitate. So what that means is that if we don't have sodium chromate, but we have potassium chromate, sodium is a spectator ion, so will potassium. We can do the exact same reaction with potassium chromate.